Hello students, this is Dr. McQueen Mendonca from the Department of Orthodontics, Vengi Shetty Memorial Institute of Dental Sciences, Nitya deemed to be University. On New Learn, we continue with the topic of removable orthodontic appliances. We notice the springs are one of the active components of a removable orthodontic appliance. I always give you the acronym for active components in a removable orthodontic appliance. SBSE stands for springs, bows, screws and elastics. We have various springs, we have various bows, we have various screws and elastics. This component of the removable orthodontic appliances causes tooth movements, active tooth movements. So we will be talking about this topic under the classification, various types of springs and the requirements. And this springs as a question for your exam purpose can come as a short note or as part of a major question. Now, springs are part of the active components of removable orthodontic appliances used to bring about tooth movement. One of the most commonly used active elements for tooth movement. Now, when we come to the classification, there are various ways to classify springs depending on the presence or absence of a helix in their design, depending on whether a helix or a loop is present, and according to the nature and stability of the spring. Depending on the presence or absence of helix in their design, we have a simple spring with no helix and a compound spring with a helix which is incorporated. Depending on whether helix or a loop is present, we have helical springs with helix in their design and a loop spring. Helix or a loop. According to the nature and stability of the spring, we have self-supported springs. These springs are made up of thicker gauge wire to avoid distortion by the patient. Then we have supported springs. These springs lack stability as they are made up of thinner gauge wire. They are supported by encasing a section in metallic tubes or acrylic to avoid distortion by the patient. Now, the requirements of a spring: they should be simple to fabricate, easily adjustable, should not cause discomfort to the patient, and should be easily cleaned, and the forces required for movement of teeth should have the required amount of force to cause the movement of tooth. Some of these springs have boxing, acrylic covering above the spring to prevent any deformation. They should possess a high degree of elasticity. They should have a long range of action and should apply forces in the required direction. We'll see about this. There is something known as the Boschinger's effect. We'll see it a little later. They should apply forces in the required direction and they should deliver the optimum force. We would have seen in some other topic in biomechanics or the types of tooth movement, what is optimum orthodontic force. The springs should deliver according to the optimum force. Now, what are the factors to be considered in the design of a spring? There are three factors to be considered. One is the force to be applied, the diameter of the wire, and the length of the wire. When we go into the properties of the wire, we'll see about it in short. That depends depending on the type of wire, the thickness of the wire, or depending on the length of the wire, the spring properties vary. Now we have this formula: force proportional to the diameter divided by the length of the wire, cube of the length. How we interpret this is, if the diameter of the wire is doubled, the deflection of a spring decreases by 14 times. It becomes stronger, but the deflection decreases. The range of movement is reduced. That is, a spring made from a thinner wire generates less force and has great increase in its flexibility. Doubling the length of the wire increases the flexibility of the spring by 8 times and also reduces the force exerted. Increasing the length of the wire increases the range of action of the spring. Helices and loops are incorporated in the design to render springs more flexible and long-acting. Now we come to the various types of springs which are very commonly used. This one, some of the springs we will be fabricating as part of the practice class. This is one of the springs which we fabricate. Finger spring, also known as a single cantilever spring, useful for mesiodistal tooth movement. We'll see the parts of the spring. If you notice the spring, the helix should always be facing opposite to the direction of tooth movement. If you want to move the tooth in the mesial direction, the helix should be facing distally. This spring is useful for mesiodistal tooth movement. Now we come to the parts of the spring. We notice that it has an active arm, a helix, a retentive arm and a retentive tag. The helix should always be facing opposite to the direction of tooth movement. The internal diameter is anywhere between 2 to 3 millimeters, generally 3 millimeters diameter. The active arm length should be about 12 to 15 millimeters. The retentive tag generally is incorporated in the acrylic base plate. Now, a few slides back I had mentioned what is something called as the Boschinger's effect. When we see the picture which you see over here, there is a first picture with a longer arrow and the second picture with a shorter arrow. Now we see that the arrow is longer. The dotted line is when the spring is activated. If you notice the difference in these two, if you have to spot the difference, the helix is opposite to the direction of the intended tooth movement in the first picture when we compare it to the second picture. In the second picture, the helix is in the same direction as the tooth movement, and we see that there is limited tooth movement here. There is limited range of action. This, in effect, is known as the Boschinger's effect. As I mentioned earlier, for a finger spring, for example, the helix should be opposite to the direction of tooth movement. It is more related to the physical property of the wire. It is known as the Boschinger effect. This sometimes is asked as a short note, or else it may be asked as a question in your Viva. The activation of the finger spring is activated by moving the active arm towards the tooth to be moved or by opening the helix. Activation of 3 mm is considered optimum when spring is made of 0.5 mm wire and up to 1.5 mm and 0.6 wire is used. It is used for the mesiodistal tooth movement such as closure of anterior diastemas. It can be used only on those teeth which are in proper alignment buccolingually along the arch. Coming to the next spring, Z spring, otherwise known as a double cantilever spring, used for labial movement of palatally locked incisors and for correcting minor rotations. It is constructed with the 0.5 mm hard round stainless steel wire. Springs consist of 2 coils very small in diameter. Springs should be perpendicular to palatal surface of the tooth, otherwise it tends to slide down and intrude it. It is activated by about 2 mm at a time, and in case of minor rotation, only one of the helices is opened. When we want labiolingual tooth movement or labial tooth movement to be more precise, both the helices are activated. And this is how the Z spring is activated. You can see this picture. The tooth moves labially. Coming to the next spring, it is the T spring. Not very commonly used. It is used for premolar teeth. With the advent of fixed orthodontic appliances, this spring not very commonly used. Yes, the Z spring or the double cantilever spring very commonly used even in the mixed dentition. If there's a crossbite, T spring in practical use not as much as the Z spring, used to affect the buccal movement of premolars and sometimes the canine. Parts of a T spring are it has two loops incorporated in the arms, retentive arms and the retentive tag. The spring is activated by pulling the free end of the teeth towards the intended direction of tooth movement. Next, we come to the coffin spring. It is a removable type of expansion, a slow expansion device, a removable slow expansion device. Methods of expansion again is a separate topic in itself. You have rapid expansion, you have slow maxillary expansion. It is used to bring about slow transverse dentoalveolar arch expansion in case of unilateral crossbite. It was given by Walter Coffin. Now we see the first picture, the way it is activated. We activate it by pulling both sides of the acrylic made in two segments large enough to make contact with all the teeth to be moved, and the spring stands 1 mm away from the soft tissues. Made of 1.25 mm stainless steel wire. It has an omega shaped wire in the mid-palatal region with retentive arms incorporated in the base plate. The retention is from the Adams clasp in the molar and the premolar. Activation is done by either pulling both the arms, the acrylic plates, or else by opening the omega loop. You see the various pictures of how it is activated, either by pulling both the arms apart or else by opening the omega loop.